Hi everyone, welcome back to Technion's ECE Deep Learning course. I'm Tal, and in this tutorial we are going to cover convolution basics with the goal of building convolutional neural networks, or CNNs, in the future. So let's begin. Okay. Hello. Okay. So we are now going to change the data we work with to images. So image data is 2D. Basically, we have the height and width of an image, but we also have the channels dimensions. So, for example, for RGB images, the number of channels is 3. So we have 3 color channels, red, green, and blue. And so basically our tensors are going to be 3D because we also have the batch dimension and the channel dimensions. Okay, that's nice. So we are now going to get familiar with some basic operation, mathematical operation, which is called convolution. And the idea is that we are going to replace the fully connected layers we were used to work with a different kind of parameters or weights, which are going to be called filters or convolutional kernels. And the idea is that these convolutional filters are going to be our weights, and they are going to extract, so each filter is going to extract features from the input image, and basically eventually we will flatten our features to a vector and use the fully connected to output our target values. But the idea is that instead of connecting all pixels to a single neuron, we are just going to assume some local dependency between the pixels, and we are going to apply some spatial operation, which is called the convolution operation, which is a moving window or cross correlation, which will be our multiplication operation. So it looks something like this, like the image here. Okay, so we'll have an image and we'll stack filters as layers. We also have other operations like pooling, which we will cover in this lesson. And eventually the idea is to downsample, so we will decrease the resolution, the spatial resolution, but we will increase the channel dimension. So basically, we are going to increase the number of filters or channels as we go down in the resolution. And this is the general recipe for CNNs, but don't worry, we will build up to it. So let's begin. So what is convolution? So mathematically, the 2D convolution over 2 signals f and h defined as the following sum, and you can see that we keep the first signal f at indices k and l, and then we multiply it by a moving window of the second signal h, which is depicted right here. So basically the idea is like moving a window and perform this multiplication between the 2 signals. Now, it's very important that in traditional signal processing, we actually do this operation, the one you see here. And what we do there is in order to calculate this multiplication, this moving window multiplication, we need to reflect the filters. Now, this is not what we do in deep learning. Basically, we kind of abuse the terms. And what we call cross correlation does not require reflection. So basically, we take this window here and marked in these four values here, and you can see that it just moves across the image, across the pixels, and perform these multiplications. Now, the idea is that our weights are going to be these values in this window, and basically in this example, the weights are just 1. So basically we just sum. So for example, the first value is the sum of 1 multiplied by 2 plus 1 multiplied by 3 plus 1 multiplied by 2 plus 1 multiplied by 1 and 1.5. And this sum is the result of this sum is 4.25. And this is the first value in the resulting cross correlation operation. Now we shift the window stride of 1, so we move 1 pixel to the right, and again perform this multiplication. and the weights here are just ones, right? So basically just the sum operation. That's the summation operation. Okay, but in practice, what we want is we want something more expressive, and we will see how we can get it. But first, let's see how it happens in practice. So we have an image, a single channel image. So for example, a grayscale image, and we have our filter, our kernel, which is a 3x3 filter, and you've seen this value of this filter just now. And what we do is we go across the image and just perform this cross correlation operation. Now, when we go out of bounds, basically we need to pad the image, and here it's just padded with 0. You can see the resulting multiplication here. And this creates the output image. So the output feature image is what goes on to the next layer, so to the next stack of filters. Now, in each layer, we are going to stack many filters because we want to extract many features. So, for example, consider images of faces, and we want to detect some features. So basically, we would want each filter to detect the different features. So we want a filter to detect the eyes, we want a filter to detect the ears, the mouth, and so on. So this is why we are going to stack many filters in the same layer. Okay, now this is what happens in convolutional neural networks. So I'll go back to this animation a bit later, but let's just now try to understand what happens here. So we have an input image. So in this case, this image, it has height and width and a channel dimension, which is larger than 3. So it can be the middle of a neural network, of a convolutional neural network. And now we have a layer with 1, 2, 3, 4, 5, 6, 7, 8, with 8 filters. Each filter performs its own operation over the image and to create the output image. Okay, so now the green filter goes on the image and to create this part of the output image. So if we have 8 filters, then the output image will have 8 channels. Okay. So you can see the new image being formed. So basically, this is the output of the current layer, and it will be passed on to the consecutive layers in the convolutional neural network. But before we actually implement that, let's cover the basics. So let's dive deeper into what is convolution and how can we use it as a feature extractor, and what is actually this operation. Okay, so in classic computer vision, we used convolutional kernels, or just kernels, to detect several properties of an image. So for example, you can see here we have the derivative kernel. So the idea is that when you run this kernel over your image, it will detect edges. So you can see what happens here. Now we set these values beforehand. So basically, this is a kernel that is not learned. This is it is constant, right? Because we implemented by hand the derivative filter. But in practice, in a neural network, these values will be learned. So basically, if our target is to classify images, then the parameters of this kernel will be tuned to detect some features. Nice. Now, recall that in order to perform well, we need good features. So we've seen this before when we picked several features. We did some feature selection to maximize the performance. But basically, usually we just let neural network learn from all of the features, and it will tune the weight such that more important features will get a larger weight. Now, basically, the idea is that we're going to do the same, just in 2D. Okay, so we need good features, right? So, for example, if you want to detect a car, you want the class to be a car, then you know that you will probably want a filter that detects wheels, detects headlights, detects the windshield, and things like that. And this is why in each layer we need multiple kernels, because we want each kernel to detect something, some features, some different features. Now, what are these features? So let's try to illustrate this with classifying cats and dogs example. How can we tell the difference between a cat and dog? So we as humans, we can just we see with our eyes, and we can, for example, take a look at the shape of the paws, at the length of the tail, the shape of the ears, and things like that. But computers, they see pixels. Pixels are just numbers, and we assume when we look at the world with our eyes, we know that there's some spatial relation between what we see and what is the object that's in front of us, right? Because we know to connect between the dots, between the pixels, at where they are located. We know how to relate the color to the location of the pixel, right? Now, raw pixels, so for example, if we have RGB, so you can think that one pixel has 3 features, right? The R, G, and B values, right? Now, this is not expressive enough because raw pixels, they do not capture the spatial relationship between the pixels. We need to assume some neighborhood around several areas in the image in order to understand what we are seeing. Now, for the other extreme, we can just connect all the pixels to a single neuron. So this is just like putting a fully connected layer. And we know that this is not a good idea because, again, this assumes that all the pixels are related to all the pixels. But this is not true, especially if we have object in the image. So extraction features from raw pixels can be done using deep neural networks, which is going to be a complex nonlinear function of the input. Now, if your data is simple enough, for example, the MNIST dataset, where we have black and white handwritten numbers, digits, then fully connected will probably work there because the data is simple enough. But when you have more colors and more complex objects, then fully connected will probably not work at all. And another problem is that fully connected layers have a lot of weights because all the pixels are connected to a single neuron. So this means a lot of weights because usually we have many pixels in an image. Now, using convolution, we can actually capture spatial structure because this is the whole idea of using a filter, and it also allows us to reduce the number of parameters greatly because filters are usually designed at spatial sizes, which are 3x3, 5x5, and 7x7. Which means that we have much less parameters, right? So this is also another advantage of using convolution. Okay, so before we discuss the building blocks of CNNs, convolutional neural networks, let's just recap what the tools that we need to do multi-class classification, because this is what we are going to do in the next tutorial. We are going to build a convolutional-based classifier, and we want to focus our discussion on the design of the convolutional layers and not the classification part, which is something you have already seen before, and we don't want to dive to that too deeply. So let's recap multi-class classification. Okay. So we are going to do this like in the recap tutorials, right? So at first we don't assume, for now you can just think of general data, non-image related data. So let's say we have some architecture that outputs some features, and eventually we end up with some vector of features that needs to be transformed into some classification vector, which is going to give us the correct label of the image of the input data we are trying to classify. So the output of the final fully connected layer in a classification model, neural network, is a vector of the length of num classes, right? Because we want each cell in this vector to give us some quantity or probability of how much the current input is from this class, right? So, for example, in MNIST or CIFAR10, which is what we're going to do in the next tutorial, we have 10 classes. So the output dimension of the vector should be 10. Now, in the output vector, we want entry I to be the probability of the input to be from class I, right? And the question we ask here is, how do we encourage the network to output the correct probability? So this is bring us back to the discussion of a loss function. So first we need to transform these unbounded values to probabilities, and the way we do it is with the softmax function. So let's cover it just really quick. So the idea is that we have something called logits. So these are just unnormalized numbers that are the output of the final layer of a neural network. And now we are going to normalize it in such a way that we will get the probability. So the way we do it is, so for example, if we have two classes and this is the output, this is the logit, these are the logits. This is the output of the final layer in the neural network. And you can see that it is just unnormalized numbers, so 1 and -3. You can think about these numbers as like energy. So the first class energy is 1 and the second class energy is -3. And of course, 1 is greater than -3, so we should classify this input as class number 1. But in order to actually train or to force the network to output these numbers, so I energy for class number 1, we need to first transform it to probabilities because our loss function requires probability. So basically, when we input 1 and -3 to to softmax, we get this for the following probabilities. So 0.98 for the first class and 0.02 for the second class. So basically, logits are energy, and we transform logits to probability with the softmax function. Now, how do we actually, now that we have the probabilities, how do we perform how do we calculate the loss function? How do we push the weights of the network to classify the first one as actually from the first class? The current input where the label is the first class. So let's see. Now that we have a vector of probabilities, we want to predict the output image. So of course, the output label. So of course, we can just take the argmax. So just important note, you can take the argmax over the pre-normalized logits. So basically, just output the logits. But the reason we need the probabilities is that is because of the loss function. So this is what we cover right now. So in order to optimize the weights to output these kind of numbers, we apply the cross entropy loss function. Okay, so let's build it. So consider we have an image of this dog here, and we have the label. So the label is class number 1, 2, 3, 4, 5, 6. So if you start your count from 1, so this is not class number 6, and if you start it from 0, then class number 5. And basically we can transform this label to one-hot vector, where it's 1 only at the position of the correct label. So at position number 6, we will have 1 and the rest is 0. So basically you can think of this y as the probability, the ground truth probability, and the ground truth probability is of course 1 only in the correct class, because this image cannot be something other than dog. So this is the ground truth label, the target. And our y hat is going to be our probabilities from the network. And now we want to bring this y hat to be closer to y. And note that when we take the argmax over y and y hat, we want them to be equal. Okay. Now, ideally, what we would want from our model to output 1 for the correct class, but we are going to work with probabilities. Now, this is the way it's going to work is we are going to calculate the cross entropy. So let W denote the weights of the CNN and W star the optimal weights. In this case, the optimal weights would be W star are the W that minimize this loss function. And what we can see is that we have X and Y are data, right? And they are labels. We have 1 multiplied by log of the correct cell, of the correct position in the probability vector. So 1 is from the ground truth. This is the original y, and PC is the output of our network, our y hat. And the reason that we only have the 1 multiplied by this cell is because the other cells of the probability vector are just multiplied by zeros, because the ground truth vector is zeros. So ideally, we would want PC equal to y hat c. Now, what happens in practice? So if we have m classes and the correct class is y hat c, so if the correct class is the phi, entry in the output vector y hat. The cross entropy function is just what we calculated here, so it's minus log PC. Now let's see how it's what is the meaning of this. So you want this entry, this fifth or sixth entry, to be 1. So this is why you multiply here by 1. Now your network the network outputs for this cell, for the fifth cell in y hat, is 0. This means that your ground truth is 1 and your network predicted probability of 0, and this makes the loss function minus log 0, which is infinity. This means your network made a critical mistake because it got the output completely wrong, right? Now let's take the other extreme. So let's say if your network predicted a probability of 1 for this entry, then the loss is 0, exactly what we wanted. So this is super. But in practice, we will get something in between. So we can say that as we get close to 1, then the loss is lower, and as we get close to 0, the loss is higher. So basically, you want to push your network to predict a high probability for the correct class. And this is the idea of cross entropy. And of course, you take this over the entire batch, where you get multiple examples, right? So at inference time, so this is what we require for training the network. But at inference time, you can just use the argmax, because you don't care about the probability, unless you care about the probabilities, but usually you just want to give the correct, you want to give the prediction of your class, and you don't need probabilities for that. You can just take the argmax over the logits. Cool. So this was just a recap of multi-class classification. Let's now go back to convolution. So what we are going to do now, we're going to talk about basic building blocks of convolution, and basically we'll talk about several operations that are part of the convolutional neural networks. And the basic ingredient is, of course, the kernels themselves, the filters. And basically we're going to stack them in layers. So we are going to put in each layer many filters, so each filter hopefully will detect different feature, and we are of course going to have a couple of layers, and in each layer we will probably decrease the resolution. Okay, so we will increase the channel dimension and decrease the spatial resolution. So we will see that in practice. Okay, now I'll just note that convolution are mainly used for image dataset, but some other areas use also convolution. So for example, in NLP, you can use the 1D convolution, one-dimension convolution, and you can also work on 3D data. So 3D data like meshes or something like that. You can also use 3D convolution. But in this tutorial, our focus is images, so 2D convolution. Okay, now the basic principle of CNN, we will now cover several basic blocks which are important, and we will use them in the following tutorial. So the first thing we need to understand is what is feature mapping and multiple channels. So the weights that are learned inside a neural network are deterministic. Once you finish your training, that's it. The weights are constant, and they have a deterministic value, right? So in CNNs, the filters after you are done training, they have constant values. Now each individual filter, it detects some certain feature. So in the first layer, for example, you have a filter that detects the nose, and the second filter detects the eyes, and so on. Okay. In the case of images, we want to mimic what we do with our eyes. So we want to detect objects or parts in order to understand the full image, the full picture. And this is where the name feature mapping comes from, right? Because of this, any convolutional layer needs multiple filters which are trained to detect different features. Now, so as we learned in the previous tutorial, to learn different filters, we need to initialize them differently, because we want each filter to detect something else. So we can't initialize them with the same weights because the training process is deterministic, and we want to learn different weights. So initialization is super critical here. Another term we need to be familiar with is pooling. So as I just said, the general recipe of CNNs is that we are going to start at a certain resolution. So you have images of certain resolution. And as you go deeper in your network, the spatial resolution is going to be decreased, but the channel dimension is going to be increased. So basically, for each area of the image, you increase the number of features you extract from it. Okay. And one of the, so usually we call this downsampling, but we can also refer to it as pooling. The idea of pooling is to reduce the spatial dimension. And the idea is that there is a sliding window that performs some mathematical operation over inside this window. So for example, in a window of 2 by 2, we can perform an operation called max pooling. And inside this window, we just take the max value. So you can see that this input is 4 by 4, and when we apply the max pool with 2 by 2 window, we actually reduce the resolution to 2 by 2. Nice. Now, there are two main benefits to pooling in CNNs. So the first one is it reduces the number of parameters in your model because it downsamples the image, and if you have a fully connected layer, then eventually you'll need to flatten your features, and in order to reduce the number of parameters in the fully connected, you want to reduce the input, and the way you do it is by reducing the spatial dimension, because if you flatten 4 by 4, then you get 16, and if you flatten 2 by 2, you get 4. So the number of weights in the fully connected layer will of course be affected by this size. The second benefit is that pooling, it actually makes feature detection more robust to object orientation and scale changes. So this is also another benefit. So you can see here that if we change or rotate the feature, so if we rotate it 1, 1, 5, and 6, then so for example, we would have 5, 6, 1, 1, the output will be the same, even though we rotated the features. So pooling makes the network a bit more robust. Now, max pooling is the most popular one, but we can also see mean pooling, average pooling, and more in general, LP pooling. So to sum up this pooling part, so pooling generalizes over lower level or more complex information. In the case, so we can ever run an example of the digit 9. So you know that that if you change the orientation of 9, it can turn accidentally to 6. And we want to be robust to the rotation. Okay, so if we slightly change the rotation, like by really small number of degrees, not 180%, 180 degrees, then the pooling operation can help us be robust for the detection of 9. Okay? And basically, pooling helps us generalize, and we will see it a lot. Now, more terms that we need to cover are strides and downsampling. So basically, in this example here, I told you that by performing pooling, we reduce the resolution from 4 by 4 to 2 by 2. But what I did not tell you is that we actually moved the window by 2. So the window first was the red one, and then the green one. The stride was 2 and not 1. We did not move 1 pixel to the right. We moved 2 pixels to the right. So this is why usually the pooling is called the max pooling is 2 by 2, because 2 is the stride and 2 is also the size of the window. Okay, so basically we move in the direction. The stride determines the number of steps we take in the XY coordinates. Okay, now when the stride is greater than 1, when you move your filter in a stride which is greater than 1, so not only max pooling, you can have just a learned filter, and you move it with a stride that is greater than 1, the resolution will decrease. Okay, the output size will be reduced. As you can see in this example below, we have a filter, and it moves with a stride of 2, and basically the resolution is decreased. Another thing we are doing is padding. So as you can see here, we are padding in order for the multiplication to be correct, right? So basically we are dealing with the edge case of the boundaries. Now, the reduction of the resolution is a good thing. It's called downsampling, and it can potentially reduce the number of trainable parameters, as I just explained before. And basically, it makes our model more robust. Okay, so padding, what is padding? So this is called zero padding, right? And the idea is that we are going to make the effective size adequate for the filter. Okay, so if there is a mismatch between the size of your input and the size of the kernel, so one is odd and the other is so we have odd and even number, odd and even size of dimensions, then you need to match. You need to pad such that they match, right? So what we do is we pad the input. So here we did zero padding. Now we actually have names for types of padding. So we have zero padding, we have reflection padding, we have replicate padding, we have more. And we'll discuss them in the next tutorial. But padding, what you need to know about the role of padding is that it is also used to retain or enlarge the dimension of the input. So sometimes, so here we are going to cover classification, but there are networks that are generating images, and in this case we need to do some upsampling. So we need to increase the resolution in the network. So basically we can play with this padding value in order to enlarge the image. But there is also a very popular kind of convolution, which is called convolution of type same. Perhaps you have seen this before, and the idea is that we pad the input such that after we apply the kernel, the output size, the output dimension does not change. And usually we are doing, in order to reduce the resolution, we will do a same padding. So basically we will pad the input such that the output won't change dimension. And in order to reduce the dimension, we will use max pool. So we will see this as well. Now, finally, sometimes you won't see it, but usually after we applied and extracted features with these convolutional layers, we have a couple of options what to do with it in order to classify the final feature vector. So you can actually directly use the output features with some classic classifier. So we can, for example, learn SVM or logistic regression, but we usually don't do that. What we usually do is put a fully connected layer, and the fully connected layer transforms our feature vector to a feature vector of size where the size is the number of our classes, right? Now, sometimes you won't see a fully connected layer. Sometimes you can see something called FCN, fully convolutional network, and it does not use fully connected at all. So, for example, you can design the convolutional kernels such that the final output is a tensor of size of shape num classes 1, 1. So basically, you reduce your pixels you reduce your feature maps to be of size 1 pixel by 1 pixel. And the channel dimension is going to be of num classes. And basically this means that you have a single vector here, because this is just dimensions of 1, so you can just transform or reshape it to be of size num classes. So basically if you did this, you don't need another fully connected layer, and essentially you can reduce your number of parameters. But usually what we do is we take these features, these 2D features, and we flatten them, and then we just pass them to a fully connected and continue as usual, like we did in the MLP tutorial, just the same. Okay, cool. Now, what we need to, as the designers of CNNs, we need to understand what is the input and output dimension of each layer, because eventually you need to, if you decide to put a fully connected layer, you need to understand when you flatten the vector, when you flatten the 2D features, what is the shape of the flattened vector. So you need to calculate it. And the way to do it is to just understand how convolutional layer works. So let's define the width of the input, W in. So basically we can also, so usually we assume symmetrical images. So W in equals age in, the height but it doesn't have to be like that. The formula is the same, but for simplicity, we just do it on the width. But yes, but since usually the width equals the height, then it's the same. So we have W, we have F, the filter size. So usually sizes are 3 by 3, 5 by 5, 7 by 7. We have the padding value, so how much you pad, and you have the stride, which is how much you move across. So the convolution formula is W out equals W in minus F plus 2 equal multiplied by the padding divided by the stride plus 1. So why 2? Because padding is symmetrical. So when you input the padding of 1, then it pads on both dimensions, right? Both on the height, on both sides of the image. Okay, so let's do a proper example. So for example, MNIST images. So MNIST images are 28 by 28. And now we're going to apply filter of size 5 by 5 with a padding of 2 and a stride of 1. Okay. So according to this formula, we get the W out is 28 minus 5 plus 2 multiplied by 2 because the padding is 2 and we have the both sides, right? And the stride is 1 plus 1, we get 28. So basically the output dimension did not change. So this is what we call a convolution of type same, because the output dimension does not change and the padding of 2 is fitting a kernel size of 5 to result in same convolution. Now for 3 by 3 kernels, for example, then the padding of 1 will result in same padding, and for 7 by 7 then padding of 3. Okay, then we apply max pooling. Okay, and this reduces the dimension by 2. So from 28 we go to 14. Now we apply the second layer, convolution layer, and we have again a 5 by 5 filters, and again we implement the same convolution, and then we apply max pool to create 7. So this is how we reduced our spatial dimensions. Now we can flatten the 7 by 7, which will equal 49. We flatten it and just put a fully connected like we did previously in the MLP. Now this drawing right here actually sums what we talked about. So let's say we have some input features of a convolutional neural network, and you can see here that for example, for the input stage, then DE equals 3 for RGB images, just like in this animation right below. But usually, since we extract, since we increase the number of channels as we go deeper, then D-in can be very large, right? Now we have this filter here, right? And basically, we have D-out filters. So we are going to put in this layer D-out filters, and each filter dimension is, for example, here it's 3 by 3, and the number of channels for each filter is the same number of features in the input features. So this is because we create each channel in the D-out channels is created by the multiplication of this filter by all the channels in the input features. So each filter creates a single channel in the output image, and since we have put D-out filters, then we have D-out dimensions, right? And age out and W out are calculated by this according to this formula. And this is what you see here. So for example, for RGB images, we have the first filters will have 3 channels, and they multiply each RGB value to create each filter creates a single value in the output, a single value in a single channel in the output image, right? And this brings us back to the animation right here. So we have the input image here. It adds more than 3 channels. We have 8 filters in the convolutional layer, and each filter has the same dimension of the input, has the same channels as the input features map, right? And since we have 8 filters, then the output image, the output to the features map will have 8 channels as well, and each channel is created by a single filter. by performing this multiplication that we see in the cross correlation. I hope this is clear. And what we'll do in the next tutorial, we are going to implement a neural network, a convolutional neural network. And basically what we'll see is when we train the neural network, you will be able to see that each filter which performs this cross correlation operation, it actually learns different features. So you can see here that each filter learned to highlight a different feature. So here we highlight the leaf, and here we have some features of the ladybug. Eventually we go down in the resolution and we increase the channel dimension, and eventually we will just perform classification to classify the ladybug. Okay, and you can see that it's important to have multiple layers because each layer operates on different resolution, and as we go down in the resolution, we are able to capture more information in a single filter. So basically, we can see here that while here just some part of the ladybug is highlighted, when you go down the network, you can see that we have some layers that are that actually highlight more area. Okay, nice. Now, before we end, I just want to motivate you a bit more and tell you about the applications of convolutional neural network, which are still widely used. So there are several applications in computer vision for convolutional neural networks. Several popular tasks include object detection. So we have an image and we want to detect objects, so it includes regressing some bounding boxes and classifying each bounding box. Okay, so each bounding box has values of the height and width. So this is just this rectangle over here. Now, another task which is usually using a fully convolutional network, so no fully connected at all, no regression, no fully connected layers here. Basically, the idea is to take an image and we want to classify each pixel. So each pixel will belong to a class. Okay. Another task is super resolution. So basically, we want to increase the resolution using convolutional neural networks. Another type is style transfer. So basically, you have an image and you want to see the same concepts but in the style of Van Gogh. So you can also do that. And of course, general image editing. We now have very strong generative models which allow us to perform editing to images. And most of these applications are based on convolutional neural networks. Of course, we can generate images. So this person does not exist. It was used with a network called StyleGAN, and StyleGAN, the generator is based on convolutional neural networks. And again, we can combine also vision with other signals, for example, audio, but this is beyond the scope of this course. Okay, so thank you for watching. This is it for the first part of convolution. In the next part, we are going to actually build new convolutional neural network, and we will have a lot of fun. So thank you for watching.